Great, I think it's time to start. Welcome to the second lecture. Today we will continue with developing the standard theory of computation. Hopefully at the end we will get to something new, which is our first successful construction of a self-referencing program. But let's see how time goes. So just a small correction from last time. Was about enumeration. Like actually in standard literature, enumeration refers to a surjective mapping, not a bijective one. So we will, let me just write it down. We say that f from n on to s is an enumeration if it is a surjective map. Not necessarily a bijective map. That's what I was saying last time. I think this will be more useful, or yeah, it's going to make things a bit simpler. So just a remark or a reminder is that last time we constructed an effective bijective enumeration of sigma star for sigma some finite alphabet. And yeah, are there any questions regarding last time? Amazing. So the remark is that it is straightforward to generalize the effective bijective enumeration to finite Cartesian products of this set. Remark. It is not difficult. To construct an effective bijective enumeration of sigma star times sigma star, or analogously, or yeah, doing the product n times. And this will actually be your first exercise. It should be nothing new, really. And last technical remark before we start doing something substantial is that it's going to be useful to sometimes talk about Turing machines or partial computable functions with multiple inputs and outputs. And the thing is, we can generalize the definition in a straightforward way. There's multiple ways to do it, so we can readily generalize the notion of a Turing machine to define a computational process with multiple inputs and outputs. For instance, instance, we can introduce an extra tape symbol hashtag. And represent each tuple x1, xn from sigma star to the power of n on the tape as one consecutive string of non-blank symbols like this. So this will allow us to talk about partial computable functions psi from some sigma star to the power of n to sigma star to the power of m. And since we have effectively enumerated sigma star, we can see those as mappings. Okay, they're partial, so I have to get used to writing that. We can see them as maps between powers of natural numbers. So now we can start effectively enumerating a more interesting set. That is the set of Turing machines themselves. It's interesting, we have just defined one definition and now we keep manipulating things, but sometimes just manipulating things syntactically gives really interesting results. So, effective enumeration of Turing machines. So this will essentially have two steps. We will first assign to each Turing machine a string from some fixed alphabet, and then we can enumerate those strings or map them to natural numbers. So each Turing machine T with some states, input symbols, and transition function is completely characterized by a finite set of instructions so each instruction is just a 5-tuple which says if I'm currently in state Q, reading tape symbol S, I should get into Q prime, write S prime, and move, where Q is from Q, S is from sigma prime, and delta Q S is Q prime S prime A. And if we want, we can also consider this as a sequence of instructions that we order in some way. So now what we can do is let us fix once and for all an alphabet which will contain the symbols 0, 1 at delimiter and parentheses, for instance. You could choose your favorite set. And we're going to completely characterize the Turing machine by a sequence of symbols from this alphabet in the following way. So, first, we represent each symbol by a unique sequence, which we can, for instance, denote Q bar from from just 0, 1. For instance, with the following convention, that Q0 bar will always be 0 and Q halt bar will always be 1. So similarly, we represent each tape symbol as from sigma prime. Again, by a unique sequence S bar, also just using these two symbols. Like for instance, we can say that the blank symbol bar will be 0. So note that the uniqueness here means that if two symbols here differ, they will have different representations as the binary sequences, but we can have the same sequences representing states and tape symbols. It's not a problem. And lastly, we represent L prime, for instance, as this sequence, L bar, S bar as this sequence, and R bar as this sequence. Now this gives us so this means we can encode each instruction Q as Q prime S prime A as we encode the state, we encode the symbol, we encode the new state. Okay, this should be now the symbols from our alphabet S. We encode the new state, and we encode the movement. And this is now really a sequence of symbols from S star. So just as an example, though I think it's very clear, for instance, if we have 0, 0, 1, 0, 0, 0, 1, represents, so example, the instruction if we are in the initial state and we are reading the blank symbol, Then we should move to the halting state, write the blank symbol, and move right. So we're almost done. Therefore, T is characterized by a sequence of encoded instructions So here, each dot is just a binary sequence. And just to know where is the beginning and end of such a sequence, we can put it again in parentheses one more time, for instance. This is so definition. We will denote this sequence, or we will, by T in brackets and call it the standard description of T. So this should really align well with our intuition from programming, where choose your favorite programming language. Whenever you write a program, you essentially construct a long string in a sequence of allowed symbols, and this is what fully represents your program. And once you let the program be executed, it's like the Turing machine suddenly implementing the computational process which maps inputs to outputs. So this should really kind of highlight the intuition that each program corresponds to some Turing machine, and it's pretty standard to see those as static objects corresponding to strings. This is completely unnecessary to put it there. So, an observation is that there exists a Turing machine which recognizes whether a string is a valid description of a Turing machine. So what this means is that if there exists some Turing machine such that S bar is the description of T, then it outputs as 1, for instance. And if there is no such t, or like otherwise, it outputs 0. So here I'm starting to do something criminal. Now I'm really associating the Turing machine to the function it computes. Like, this is pretty standard, but you should still keep the distinction in mind, right? So this should not be so hard to see. So essentially, this TM needs to check the syntax. So, for instance, that S begins and ends with the begins with this and ends with this symbol, that it consists of like solely of sequences of the form one, two, three, four, 5, where each of these is just a binary string. And finally, it has to check that this sequence really represents or defines a deterministic function with 2 inputs and 3 outputs. So, and that it represents a deterministic function with 2 inputs and 3 outputs. So in your favorite programming language, you could easily write a code that checks this. So this brings us to the following pretty important theorem. Let Tm, which is a subset of S star, be the set of all of standard descriptions of all Turing machines. Then there exists G, a map from N to Tm, which is a total computable bijective function. So it could be a theorem or a definition, because the proof is not so hard. So we define a Turing machine G with some states, with the alphabet being exactly S, with some transition function delta, which implements G. And we do it as follows. On some input n. So first set a counter on the tape to 0. Start enumerating sequences from S star. So we have an effective enumeration of S star, so yeah. Starting from the smallest. Whenever the sequence represents a valid DM description, increase the counter by 1. So here, enumerate the sequences means it writes it on the tape and then rewrites it with the next one and then rewrites it with the next one. So once the counter equals output the current sequence. So now we will also have to accept that in a lot of proofs, when I define a Turing machine, and I only do it in a very high level of description, and hopefully you can always persuade yourself that if needed and you were stranded on an island and had nothing better to do, you could turn it into an actual Turing machine definition. But as long as you know that you could write a program that does this, it essentially means there is a Turing machine that can implement it. And yeah, essentially, this gives us a guarantee that this Turing machine G will output exactly the nth valid description of a Turing machine. And since each description is finite, it's going to eventually be listed for some n, so this is really a bijection. So an observation is that the inverse is also a total computable function. Just because sometimes we will use it, it's pretty straightforward that if you have a total computable bijection, the inverse is also total computable. Good. So crucially, G is called the Gödel numbering, or Gödel function. For for a Turing machine t with g of n being exactly the description of t, we say that n is the Gödel number of t. So this is an, I suppose, in honor of Kurt Gödel, who went through the laborious process of encoding sequences and proofs and a hierarchy of objects of higher and higher complication into the natural numbers. So now we encoded Turing machines into natural numbers via this Gödel function. And I suppose one of the most important definitions in these 2 weeks so let U be a partial computable function defined as U on input I n is phi with index I applied to n is called, okay, so U is called the universal partial computable function. And any Turing machine U that implements it is called a universal Turing machine. So is this a definition or a theorem? We should technically check that U is truly a partial computable function, right? So technically, we should check there exists a TMU, at least one, implementing the function U. But that should be clear thanks to the work we just did. So define U on input I n as follows. So first, compute. So I is a Gödel number of some Turing machine, and we can use the Gödel function to give us the description of that Turing machine. And then using the instructions from the description of T, simulate what T would do on the input n. Simulate T on input n. So why is this crucial? Suppose we are interested in the 1930s to build actual computers, and we kind of accept that Turing machines are the right definition of what a computer or computational process is. Before, we would have thought maybe that if we want to implement addition of two numbers, we have to physically build a Turing machine that specifically does addition, and if we want to do another function, we have to build a different Turing machine. But this is actually not the case. Essentially, Turing, with this universal machine definition, predicted the organization of a general, a fully general computer. Essentially, all we have to do is build one specific computer which implements U. And then, as we give inputs to it, we essentially split the memory into two parts. One which encodes the description of the program we would like it to execute, and another one that actually contains the data that we would like it to execute on. And this is exactly the von Neumann architecture in modern computers. And it is indeed historically well documented that when von Neumann did build the first general fully electronic computers, he did credit Alan Turing for this notion. Great. So now let's delve back into some technical remarks. So each partial computable function phi, well, we know that there is a Turing machine that implements it, but there's actually not just one, but infinitely many of them. Not by one, but infinitely many different Turing machines. And in fact, given the description of some Turing machine which implements it, we can build a Turing machine that will list all the other Turing machines, or infinitely many Turing machines that implement it. Not necessarily all, but yeah. We can effectively generate infinitely many of them. So what is the intuition behind it? Suppose T implements this function, and we have the sequence of the instructions. We can just arbitrarily extend the state space and the symbol space by additional symbols, and we can make up arbitrary instructions to pad the description of T with, and these will never be used during the computation, right? Because T will never visit them. And in this way, we can create the description, an arbitrarily long description, which is a valid description of some other Turing machine, which computes exactly the same function. So this can be summarized in the following padding lemma, which will say nothing new after what I have just said. So there exists a total computable function we can call it P, like the padding function, which maps tuples of integers into n such that if P on some input NA is n prime, we have that phi of n is equal to phi of n prime, and n prime is larger than a. So what does this say? This basically says if you interpret the first input as the Gödel number of a Turing machine and the second input as some lower bound, then this function will generate the Gödel number of a different Turing machine which computes the same function as n, but whose Gödel number is as large as you want it. Yes? So we define a Turing machine P which implements P as follows. So on input n a, compute the description of the Turing machine with the Gödel number n. Let's say pad, we can say pad. Pad T with arbitrary extra instructions so that we get a valid description of some other Turing machine, and this description is long enough so that if we compute the Gödel number of this description T prime, it holds that n prime was larger than a.